So let's start with the question. Okay. So in this question, we have an elliptical orbit, and whenever there is an elliptical orbit, you can either remember the formulas, or a better way to approach elliptical orbit is just remember two equations. Okay. Energy equation, that means the total mechanical energy will always remain conserved, isn't it? Because the only force that is acting on the planet is gravitational force, that is conservative in nature. So the total mechanical energy in an elliptical orbit will always remain conserved. Okay. So first thing you need to remember is conservation of mechanical energy. Conservation of mechanical energy. Okay. Mechanical energy means kinetic energy plus potential energy. Okay. And the second thing that you need to remember is conservation of angular momentum. Because at every point in the elliptical orbit, the angular torque or the total torque acting on the planet is equal to 0. So conservation of angular momentum. Conservation of angular momentum. So whenever there is an elliptical orbit, just either follow these two equations. Okay? Conservation of mechanical energy, conservation of angular momentum. And your questions will be more or less solved. Okay. So in this question, this is an elliptical orbit. Okay. This is an elliptical orbit. Now this is a planet A. Okay. Moves around the elliptical orbit, and the main mass of the elliptical orbit is Sun. Sun is around out here. Okay. Fair and fine. Now at any distance, that means in this elliptical orbit, say at this distance or at this distance, at any one of the distance, when the position vector from the planet, of the planet from the Sun was unknown. That means when the planet was out here. Okay. When the distance or position vector is unknown from the Sun, its velocity vector was equals to V0. That means the velocity vector of this planet was equals to V0, isn't it? And one more information is given. The angle between position vector and velocity vector was equals to alpha. That means the angle between position vector and velocity vector is equals to alpha. Okay. So what is given in the question? It is given that at certain point in the elliptical orbit, the position vector from the Sun was unknown. The velocity vector in the elliptical orbit was equals to V0. Okay. And obviously these two velocities and this position vector is from the frame of reference of Sun. That means our Sun is the origin out here. Okay. And the angle between R0 and V0 is nothing but alpha. What we have to find out is the minimum distance of the planet from the Sun. Okay, this planet A from the Sun. That means in this elliptical orbit, there will be many distances. Okay, out here the distance is this much, out here the distance is this much, out here the distance is this much. Okay, we have to find out the minimum distance. Okay, this minimum distance. Let's name this R. Okay, so at position vector R, when the planet was this point, okay, minimum distance will always form at this point. No, minimum distance is always at this point, and maximum distance is always at this point. So at minimum distance, okay, the velocity vector was given as, or let's assume the velocity as v. Okay, obviously I need to find out the value of r. The value of v would get cancelled out by these two equations. Okay, we need to somehow cancel out the value of v within these two equations and find out the value of r. Fair and fine. Okay, now what we have to do out here is just apply our equation. I'll apply my first equation, conservation of mechanical energy. Okay, so initial mechanical energy, let this be 0.1, let this be 0.2, or initial final. Okay, doesn't matter. The total mechanical energy at every point is same. The angular momentum at every point in the orbit is same. So doesn't matter when we apply 0.1 or 0.2, initial or final. Okay, let's say this is 0.1. Let's say this is 0.2. Okay, so total kinetic energy at point, or let's say this is point A, B. Point A, point B. So total kinetic energy at point A is nothing but half mv square, isn't it? Minus total potential energy at point A is nothing but g mass of Sun into mass of planet divided by r. So g mass of Sun into mass of planet divided by r, where r is the radius of apogee, isn't it? Sorry, perigee. Okay, is equals to the total mechanical energy out here should be equals to total mechanical energy out here. What is the mechanical energy out here? Half m v0 square minus what is the potential energy out here? G mass of Sun into mass of planet divided by this radius vector, or r0. So this is my first equation. So let me just make this first equation neat and clean. Okay, m, this m and this m would get cancelled. So let's cancel out this m, isn't it? Okay, so this is my first equation. And what is the formula for my second equation, or from where do I get the second equation? Conservation of angular momentum. So the total angular momentum out here, obviously my origin is at the Sun. Okay, my origin is at the sun because this R naught, V naught, okay, R, V is defined from the frame of reference of sun. Okay, so angular momentum out here of this planet is equal to angular momentum of out here of this planet. So number 2, conservation of angular momentum. Conservation of angular momentum. So what is the angular momentum out here? AM R cross V out here, AM into R cross V. R cross V is nothing but R, magnitude of R into magnitude of V into sine of angle between R and V, isn't it? And what is the angle between R and V at minimum distance? Is 90. The angle between R and V out here is 90. The angle between R and V out here is 90. And these are the only 2 points where we get 90. Okay. So AM R V sine 90 is equals to, what is the total angular momentum out here? AM into R naught cross V naught. R naught cross V naught is nothing but magnitude of R naught into magnitude of V naught into sine of angle between R naught and V naught. And what is the angle between R naught and V naught? Alpha. So R naught into V naught into sine alpha. So out here also mass and mass will get cancelled, and this is our second equation, isn't it? Now solving this first and second equation, we'll get the value of R, or the minimum distance in terms of this V naught and R naught. Okay, and mass of sun M. So let's solve this equation, or let's solve these 2 equations. Okay. Now solving this 2 equation that I got out here, okay, I'll get the value of R, or the shortest distance. Okay. Now I can directly give you the answer, but just I'll show you briefly how to solve these 2 equations. Okay. And this will be done in a quick manner. So these are the 2 equations I must solve. Okay. These are the 2 equations that I got from here, and I must solve, isn't it? Okay. Now the first thing that you have to do is from the second equation, okay, RV is equals to R naught V naught sine alpha, or conservation of angular momentum. From this equation, just take V is equals to R naught V naught sine alpha by R. Let me send this R to the downward. Now substitute this V out here in this V square. Okay, substitute this V in this V square, and then you get some equation somewhat like this. Okay, when you substitute the value of V square, you get an equation somewhat like this. Okay, now what do you have to solve for? You have to solve for the value of R, isn't it? Now to find out the value of R, multiply this entire parameter, or this entire equation, by R square. This entire 4 parameters by R square. So when you do that, we'll get somewhat like, or something like this value. Okay. And now see, I multiply this term by R square, you got a term of, see, this R square got cancelled. If you multiply this term by R square, you get a term of R. If you multiply this term of R square, you get R square out here. Out here, you get R square out here. So multiply the entire 4 terms by R square. Okay. The purpose of this is, if you do this, okay, now you get a quadratic equation with R square, or as a value of R square. Okay. Now the next step out here is nothing but take GM by R naught common forcibly from all these 4 parameters. From left hand side also, from right hand side also. There's a doubt you might have. So there is no parameter of GM out here. Okay. So when you take GM by R naught common from this, or if you exclude from this, you have to multiply this parameter by R naught by GM, isn't it? So forcibly take GM by R naught common from all these 4 parameters. So when you do that, we'll get some equation like this. Okay. What I did out here is I took GM by R naught common from all these parameters, 4 parameters. Okay. If you take GM by R naught from first parameter, you get every term except you have to multiply by R naught by GM. That which I did out here. Okay. Out here GM and GM will get cancelled, isn't it? And out here R naught will get multiplied by R naught. So if you multiply this term by GM by R naught, will get this term. If you multiply this term by GM by R naught, will get this term. Okay. Similar kind of thing you have to do on the right hand side. Take GM by R naught common, we get this term. Okay. And one more thing, on the right hand side, we'll get R square also common. So take common R square also. Okay. So if you multiply this term and R square, we'll get this term. If you multiply this term and this term, we'll get this term. Okay. So the first step is multiply this entire 4 equation by R square. The second step is take common GM by R naught. Now when you cancel this GM by R naught, what will happen? The next step is we'll get this kind of equation. Okay, we get this equation. I just cancel out the GM by R naught part. Okay. Now this equation I'll copy in next page. Okay. So this is the equation that I got out here. This is the equation that I got out here. Okay. Now in this equation, since this equation is getting very complicated, I'll do one more thing. Okay. I'll simplify some term. Simplify some term means take this term, for example, V naught square R naught by GM. I'll take this term as N or any other variable. Okay, it doesn't matter. Take any other variable as A. Okay. Let's take V naught square R naught by GM as A. Okay. Assigning the value of R naught V naught square by GM as A. Now when you do that, I'll get some term somewhat like this. Okay. From the first term, it is nothing but V naught square R naught R naught cube can be written as R naught into R naught square, isn't it? So n into R naught square into sine square alpha by Gm. Gm is already included in this n. Okay. So when you take or when you assign R naught V naught square by Gm as n, you'll get this term, isn't it? Now if you observe very carefully, this entire term became more simplified. Okay. Now what you can do is out here you can take this entire term to the right hand side. Okay. This entire term is taken to the right hand side. Now, if you observe this, this is nothing but the form of a r square plus br plus c. Okay, or quadratic equation in the form of ax square plus bx plus c. Okay, the root of quadratic equation with ax square plus bx plus c is nothing but minus b plus minus under root of b square minus 4ac by 2a. That was the root of quadratic equation. Similarly, if I form a quadratic equation with the variable of r, okay, what do I get? I'll get this, or what? The answer, I'll get the answer, isn't it? But before jumping to the answer, let's do one more thing. Let's multiply the entire term by minus 2. Okay. Now you're asking why. See, if you do this also, it is correct. If you multiply this entire term by 2, then also it's correct. If you multiply the entire term by minus 2 also, it's correct. Okay. But the answer that you get in irodov or the back of irodov is nothing but they have taken minus 2, or they have multiplied this entire equation by minus 2. Okay. Multiply this entire equation by minus 2. Okay. This much is understood. Okay. Now when you multiply this entire equation or entire quadratic equation by minus 2, what you'll get is, you'll get some term like this, isn't it? 2 minus n r square, and this is more simplified form of ar square plus br plus c. Okay, ar square plus br plus c. This is the quadratic equation. The value of a out here is nothing but 2 minus n. The value of b out here is nothing but minus 2 r naught. The value of c out here is nothing but this entire term a n r naught square sine square alpha, isn't it? Okay. So I got this term. Okay. Now I just have to solve for the value of r using the formula for quadratic equation. We already know that r, okay, or the value of quadratic equation. Just let me find my pen. Okay. Value of r is equals to minus b plus minus b square minus 4ac by 2a. This is the root of quadratic equation. Okay. Isn't it? So r is equals to what is the value of b? The value of b is nothing but minus 2 r naught. Minus 2 r naught plus minus the value of b square, or minus 2 r naught whole square, minus 4. The value of a is nothing but 2 minus n. 2 minus n. And the value of c is nothing but n r naught square into sine square alpha. Just let this, or let us write this term as c only. Okay, it won't make a difference out here. C. Okay, by 2a. 2 into 2 minus n. Okay, now see. This minus and this minus will become plus. So this minus and this minus became plus. Okay. Now if I take, I can take minus 2 r naught whole square is nothing but 4 r naught square. Minus 2 r naught whole square is nothing but 4 r naught square. And if you take 4 common from these two terms, okay, and take it outside the square root, it will become 2. Okay. So that 2 and that 2 and this 2, if you take common and cancel it by this 2 from the denominator, that means what I'm doing is I'm taking this 4 common inside the square root. If I bring this 4 common outside the square root, it becomes 2. Now I take this 2 and this 2 common and cancel out with this 2, isn't it? So this 2 and this 2 would get cancelled. Understood this much? Now r is nothing but r naught plus minus r square minus 2 minus n into c. The value of c is nothing but n into r naught square into sine square alpha. N into r naught square into sine square alpha by 2 minus n. By 2 minus n. Okay. Or I can also take r naught square common from inside the bracket. Okay. So I'll take r naught common, 1 plus minus under root of 1 minus 2 minus n into n sine square alpha by 2 minus n. By 2 minus n. So this is our answer that we get. Okay. This is the answer that is given in the back of the. And this is how we solve this question. Okay. So the general concept out here is, the main physics that ended out here is nothing but whenever elliptical orbit comes up, the two equation that you can apply is conservation of mechanical energy, conservation of angular momentum, and that's the end of physics. The entire rest of the things are nothing but solving of these two equations. Okay, this can be tough, but nonetheless you have to have the aptitude. You have to somehow develop the aptitude for solving equation. Okay, by practicing a lot. There's no one that can teach you. See, for this specific problem I showed you, what to take this one common. But the main question that you get, or the question that you get in exam, might be different from this two question that I'm going to you. So somehow develop a aptitude for solving equation. Okay, the rest of the problems or rest of the things are nothing but easy, more or less easy. Okay, this equation, what more is there? There's no part of physics that is left out there, no. So instead of having this approach of formula substitution that you do in class 10 kind of thing, just now develop a habit of equation solving. Okay, so the equation that you make and solve the equation. That from formula substitution or formula, then put the values in the formula and then solve the question. Instead of that approach, try to develop this kind of approach. It will be much more helpful to you. Okay. Now in this question, okay, there is a central star out here. That means there is a very heavy star out here. Okay, and a planet is moving in a straight line in the star. Okay, I'll just explain this question in a simplified manner. That means just read the question once. The question will be explained in a simplified manner. And the question says that there is a very heavy central star out here. Okay, and a planet. Okay, the mass of this planet is very less compared to this star. That means this the same theorem of circular motion and elliptical motion will be applied out here. Okay, problem is out here, instead of being in an elliptical path, what happens is it is going in a straight line. Okay, and the approach, that means aiming parameter, that means what, when this goes in a straight line, sometimes every star or every planet is not captured by sun, no? Or every satellite is not captured by any planet. So what happens is they deviate their path by a little bit. Okay, and that kind of path is known as parabolic path. Okay, but right now, sir, you said only elliptical path and circular path. What about parabolic path? I also said something about eccentricity, no? So when the value of eccentricity becomes more than one or more than one, okay, then that ellipse turns into parabola. Understood this much? Okay. Parabola means, that means when the value of eccentricity is greater than 1, that means what will happen is this planet will go deviate its path and go in this direction. It will never come back in an elliptical orbit. Okay, it will never make an orbit or complete orbit. Okay, it will go out here, deviate its path and go back. Now the aiming parameter, or the parallel distance between the velocity vector and the star, is given as L. Okay, this is nothing but the aiming parameter. The question is asking what is the distance of closest approach. That means what is the minimum distance from the star. That means in this entire path, okay, of the planet, the minimum distance of the planet from the star would be out here. We have to find out this distance r. Okay. So whenever there is an elliptical orbit, what did I say, or circular orbit, or whenever there is a heavier mass and the lighter mass is moving in an orbit, what are the two equations that we can apply? Conservation of energy, and the second one is conservation of angular momentum. So same thing out here. You have to apply conservation of energy, mechanical energy. That means kinetic energy plus potential energy, or kinetic energy plus potential energy. And the second equation is conservation of angular momentum. Okay. Conservation of angular momentum. These are the two equations that you have to apply. Okay, or whenever there is a heavier mass, okay, and the lighter planet is orbiting around the heavier mass or going around the heavier mass. Okay, now if you check out here, okay, even though the path is parabolic, assuming my origin is at the start, or assuming my origin is out here, okay, at the start, what is the angular momentum of this planet about this origin? Angular momentum of this planet about this origin is nothing but m, mass of the planet, into v naught into L. I have already shown you in previous lecture. Okay, that any body moving in a straight line will always have a fixed angular momentum about a origin. I mean, this planet is moving with a constant velocity in this direction, isn't it? Okay, obviously the velocity will be much faster out here. It will go very slow out here. But at this specific point, what is the angular velocity? Sorry, what is the linear velocity? V naught. So if the linear velocity is V naught, what is the angular momentum? Mass of the planet into r cross v. The value of r is nothing but this one. Okay, r cross v is nothing but L into v naught. Okay, so the angular momentum of the planet at point A. We are first applying conservation of angular momentum. Angular momentum at point A is nothing but mass of planet, mass of this planet A into v naught into L. Okay, those who are confused about how it's m into v naught into L, just go and see the previous lecture of work energy power. The last few questions, this exact same thing was out here. Okay. Okay. The angular momentum out here is nothing but m into v naught into L. M into v naught into L. At closest approach, okay, when the planet is out here, the velocity vector would be in this direction. And at closest point, the velocity vector is always perpendicular to the r vector. So what is the angular momentum of the planet out here? The angular momentum of the planet out here would be nothing but m into some other velocity v into r, where r is the closest distance. Okay. So initial angular momentum or angular momentum of the planet out here is equals to angular momentum of the planet out here. Okay. So m and m would get cancelled, or v naught into L is equals to v into r. Now we apply our first equation, conservation of energy. What is the total mechanical energy out here? Half m v naught square minus gm, or mass of star, into mass of planet divided by r. Let's name this another variable instead of r. Let's name this variable x. Okay, this is nothing but x. This distance is nothing but x. Okay, x. This is the total mechanical energy at this point. Okay, is equals to final mechanical energy. Kinetic energy at this point is equals to half mv square. Half mv square. Potential energy at this point is equals to minus g mass of sun into mass of planet divided by r. Minus gm mass of planet divided by r, or the distance of closest approach, or the minimum distance from the star. Now, one assumption in this question is this x is very far away. Okay, the assumption out here is x is very large. Very large. So if this value of x is very large, okay, so this x, if this x tends to infinity, then what happens? This entire value gm by x, this tends to 0, isn't it? So our equation would be nothing but, if I make this tending to 0, the equation would be half mv naught square is equals to half mv square minus g m by r. Now we got our two equation. The first equation is, sorry, this is the second equation. This is the first equation. Now solving these two equations, we get the value of r. Okay, and the equation solving is similar to previous question. I'll just solve it a little bit quickly. Okay, so I'll just solve this equation very fast. Okay, from this first equation, I get that v is equals to v naught L by r. Now this value of v is to be substituted out here, v square, isn't it? So when you do that, we get half m v naught square is equals to half m v naught square L square by r square minus g m by r. You can cancel out the m from left hand side and right hand side. Now this is a quadratic of r. Okay. However, the variable r is in denominator. So what do? We multiply every parameter by r square. So if I multiply out here by r square, it becomes r square. Out here, if I multiply this parameter by r square, it gets cancelled. This parameter r square and r gets cancelled. We'll be left with r. Okay. So let's make this neat and clean. Okay. I get somehow our equation to be half v naught square r square. I just reverse this. Okay. Nothing new. Is equals to half v naught square L square minus gmr. Okay. Now I have a quadratic equation in terms of r. Okay. Let's multiply every parameter by 2. Let's make this equation more neat. Okay. So 2 half into 2 is nothing but half into outer 2 is nothing but this, and this gmr will be translated into minus 2 gmr, because I'm multiplying every parameter by 2. Okay. Now let's bring everything to the left hand side. Plus 2 gmr is equals to, not is equals to, minus v naught square L square is equals to 0. So this is written in terms of ar square plus br plus c. But the roots of quadratic equation is minus b plus minus b square minus 4ac by 2a, where a is nothing but v naught square, b is nothing but 2gm, and c is nothing but minus v naught square L square. Okay, so r is equals to minus b minus 2gm plus minus b square. Okay, 2gm whole square minus 4ac, minus 4 into value of a is v naught square, value of c is minus v naught square L square. This minus, okay, this minus will get multiplied by this minus and become plus. So plus v naught square L square, isn't it? Divided by 2a. 2 into, what is the value of a? V naught square. Or the value of r is minus 2gm plus minus 4 g square m square plus 4 v naught square, v naught to the power 4. See out here. Okay, this v naught square would get multiplied by this v naught square and become v naught to the power 4. So V naught to the power 4 into L square, fair and fine, by 2 V naught square. So I can take this 4 common, okay, and take it outside the square root. If I take this 4 outside the square root, it will become 2. This 2 and this 2 will get cancelled by this 2. So effectively what is happening is this 4, and this 2 are getting cancelled. Okay. So this is our answer. Now I'm going to make this equation more neat and clean. Make Gm by V naught square is equals to n. Okay. And find out the value of and substitute the value of n. Okay. Gm by V naught. See, if you make Gm by V naught is equals to n, just make Gm by V naught is equals to n. Nothing, it's nothing. Okay. So we'll get the answer or neat and clean form of the answer. So this is as it is. Now in this question, okay, there is a uniform sphere of mass n. Okay, and there is a smaller mass, point mass, located at distance r from the center of the sphere. Okay, this is distance r from the center of the sphere to small mass n. The first part of the question is asking the potential energy of gravitational attraction of the particle and the sphere. That means the potential energy of the particle and the sphere. The second part of the question is asking find the gravitational force on this particle. So this is more or less very simple question. Okay, so I'll give you the generalized theory out here. Okay, generalized theory means forces and energy, okay, or fields. See, forces and energy in electrostatics I already explained. Force on unit kg is nothing but called field. Potential energy of unit kg is called potential. Okay, so instead of writing force and energy, can I write field and potential? It will be the same thing, no? Force on mass m. Okay, suppose I reduce this mass m. Suppose I reduce this mass m to 1 kg and find out the force on this particle. Okay, it will be same thing as field at this point, isn't it? Okay, or suppose I reduce this mass m to 1 kg and find out the potential energy of the system. It will be same thing as potential at this point. So instead of writing force and energy, okay, right, fields and potential. Field and potential. Field is nothing but force on unit kg. Potential is nothing but potential energy of 1 kg. Okay, field and potential of a spherical object. Spherical object. Okay. Now, whenever there is a spherical object, be it electrostatic, be it gravitational, okay. Suppose this is mass m. There are two scenarios. I have to find out the field. That means I'm keeping out 1 kg. Okay, I have to find out the field outside the sphere, at the surface of the sphere, and inside the sphere. Okay, there are basically 3 points of discussion. Okay, point 1 is outside the sphere. Point 2 is surface of sphere. And point number 3 is inside the sphere. Inside the sphere. Okay, so this is point 1. Field and potential outside the sphere. Field and potential at the surface of the sphere. Field and potential somewhere at the inside the sphere. It doesn't necessarily have to be at the center. Okay, this point can be at anywhere inside the sphere. Okay, this is point 3. Okay, now whenever you're talking about point 1, okay, outside the sphere. Outside the sphere. So whenever you have to find out the field outside the sphere, okay, this entire sphere can be assumed as a point mass situated at the center of the sphere. So this entire sphere is assumed as a point mass situated at the center of the sphere, and you have to find out the field at this point, and this distance is r. Okay, this distance is r. R is nothing but the distance between center of the sphere to a point outside the sphere. Okay, the force at point 1 or the field at point 1 would be nothing but g mass. If you're finding out field, substitute this mass by 1 kg, 1 out here, divided by r square. You're finding out the force, substitute by mass of this particle out here. Both are the same thing. Gm by r square. See, out here I'm not writing negative or positive, just because out here I'm discussing only the conceptual parameters. Okay, the directional parameters will be discussed later. Understand the concept first. Obviously there will be minus out here, but that's later part of the answer, later part of the question. Okay, or later part of the concept. So force outside the sphere is nothing but F is equals to gm by r square, or field is equals to gm by r square. But gravitational field can be also written as g. Okay, F is equals to gm by r square. Okay, and this field is also written by g, or acceleration due to gravity at this point. Okay, this value out here is nothing but the acceleration due to gravity at this point of any mass. Okay, okay. What is the potential out here? This is nothing but the field, This is nothing but the field, gravitational field. Okay, what is the potential out here? The potential out here is nothing but gravitational potential, or potential energy, or energy of 1 kg. Energy is a scalar quantity, is equals to g into m by r. Okay, or minus gm by r. So out here, this is the potential. I'm not writing the minus sign, doesn't mean the minus sign is not there actually. Okay, just understand the magnitude of the concept. Okay, these are just the magnitude out here. So this is nothing but the field, this is nothing but the potential. Okay, let me write minus. What is that? Okay, fair and fine. Now the second scenario is at the surface of the sphere. At the surface of sphere. Okay, so let the radius of the sphere be capital R. Let's say the radius of the sphere is capital R. Okay, radius of the sphere is capital R. So even when the particle, or when you have to find out the field at the surface of the sphere, in that case also you have to assume this mass, or spherical mass, a point object situated at the center. So even at this point you have to assume this mass, point object situated at the center. You have to find out the potential and field at this point R. Okay, point number 2. So gravitational field is nothing but minus gm by capital R square. Okay, and potential is nothing but minus gm by capital R. Fair and fine. Okay, this is nothing but field, this is nothing but potential. This much is understood. So whenever the point is outside the sphere or the surface of the sphere, we have to assume this sphere as a point object situated at its center. We have to assume the sphere, entire sphere, as a point object situated at the center. Okay, and find out the potential and field by the same formula that we have derived before. Okay, now things become a little bit interesting when this point is inside the sphere. Okay, see, outside the sphere, it's the same formula as gm by r square, or gm by r, or g mass 1 into m1 m2 by r square, g m1 m2 by r. Okay, when the point is inside the sphere, what happens is, see, I'll just copy this and I'll just paste this. Okay, the third point. Okay, when the point is inside the sphere, what happens? Point inside the sphere. The point is inside the sphere. Point is inside the sphere. Now you might have a different concept out here. So this is another formula. Obviously, the formula is same. Okay, I'll just show you how. Okay, in your theory, you might have learned a different formula. See, the formula inside the space, whether you're finding field or potential, is nothing but g into mass inside divided by r square. Okay, similarly for potential, it's g, potential will derive by another formula. Okay, force is nothing but g mass inside divided by r square. Okay, so suppose you have to find out the field at this point 3. Okay, at this point 3. 3 is not at the center. The distance between center and point 3 is x. R is the radius of the sphere. Okay, what do I mean by the formula g mass inside divided by r square? G mass inside divided by r square nothing means this point is 3, no? So we encircle this point. Okay, we encircle this point from the center, and whatever mass is situated inside this circle, that will only be the mass inside out here. Okay, this is only the mass inside. Understood? So the field at point 3 is nothing but G into mass inside by r square. Now this r is nothing but x, okay, or x square. Now you might ask, sir, I have learned a different formula in class. There was a different kind of formula. See, that formula came from the assumption that this sphere, okay, or the spherical planet has uniform density. Okay, this spherical planet has uniform density. The assumption out here, or the assumption for the formula that you derived in class is planet has uniform density. Planet has uniform density. That means density of the entire planet is equals to density of this much part of the planet. Okay, and what is the formula for density? Density is equals to mass by volume, isn't it? So mass of the entire planet divided by volume of the entire planet is equals to mass of this much part of the planet divided by volume of this much part of the planet, isn't it? Because the density of the entire planet is same. Okay, so mass of the entire planet is m divided by volume of the entire planet is 4 by 3 pi r cube. Volume of a sphere is nothing but 4 by 3 pi r cube, which is equals to mass inside point 3 divided by what is the volume of inside point 3? 4 by 3 pi x cube. Now if I just take these two equation, okay, these two equation and solve it out here. So m by 4 by 3 pi r cube is equals to mass inside by 4 by 3 pi x cube. 4 by 3 pi and 4 by 3 pi will get cancelled, or mass inside is equals to total mass of the planet into x cube by r cube, isn't it? So mass inside this planet or inside this point 3 is nothing but mass of the planet into x cube by r cube. So when you substitute this one, mass inside by m x cube by r cube, you get the formula that you learned in class, which is nothing but F is equals to, field is equals to G m x cube. See, okay, x cube and x square get cancelled to become x. So Gm x divided by r cube. So this is the formula for field inside the sphere. Okay. So what happens if the sphere was of non-uniform density? Then the relation of density would be given, no? And you have to integrate it one. But the general formula for finding field inside the sphere is nothing but G is equals to field is equals to G into mass inside divided by r square. Okay. Fair and fine. Now that we have found out potential, sorry, field, we'll go to the potential. So I'll solve the potential out here. Okay. Now this is the part that most of you get confused. Potential inside a sphere. Potential inside a sphere. Inside a sphere. Okay. Achha. You already got the formula for field inside a sphere. Gmx divided by r cube. Sometimes instead of using x, they'll use depth from the surface. So depth from the surface is nothing but r minus x. So just write r minus h as depth from the surface. Both are the same thing. Okay. Now to find out potential, what is the definition of potential? Work done against a gravitational force in bringing a unit kg from infinity to this point, or point number 3, isn't it? Work done in bringing a unit kg from infinity to point 3 is nothing but potential at this point, isn't it? So you already know work done against gravitational force from bringing a unit kg from infinity to the surface is nothing but minus gm by r. So work done in bringing a unit kg from infinity to the surface is nothing but minus gm by r. So I'll make a note out here. Okay, I'll take this factor as a note. Okay, potential at surface is equals to minus gm by capital R. So what is the potential at this point? Potential at this point is nothing but work done against gravitational force from infinity to this point, from infinity to surface, plus work done against gravitational force in bringing unit kg from surface to point number 3, isn't it? See, this total work done in bringing 1 kg from infinity to surface plus from surface to point number 3 is nothing but the potential at point 3, isn't it? So the first thing is I have to find out what is the work done in bringing a unit kg from surface to point 3. Okay, so work done in bringing a point charge from surface to point 3 is nothing but f dx. Work done is nothing but force center of displacement, isn't it? Or work done is equals to, what is the value of force? Gmx by r cube. Gmx by r cube, isn't it? Into dx. Okay, dx is nothing but displacement or elemental displacement. Now sometimes instead of using x, somewhere they use the variable of h, somewhere they use the variable of x. Both are the same thing. Okay, when you integrate this one, work done is nothing but gm x square by 2 divided by r cube, isn't it? Okay. Now this is the point where most of you will get confused. What is the lower limit and upper limit of this integral? The lower limit of this integral is nothing but x, or point at the surface, and the upper limit out here is nothing but the surface of the planet. Okay, why, sir? Why are you we're bringing a point charge or point mass from infinity to this point? No, so why is the lower limit x and upper limit at the surface? See the variable that I'm integrating out here, gmx by r cube. X is nothing but distance from the center. So when I'm using distance from the center, the lower limit would be x and the upper limit would be r, no, isn't it? If you use variable out here instead of x by r minus h, so instead of using gmx by r cube, suppose I'm using the force as gm by r cube into, instead of x I'll be using r minus h. Okay, r minus h, or radius of planet minus depth, into dh. Then the lower limit would be surface of the planet and the upper limit would be depth h. Okay, understood the scenario? Okay, so now the total work done in bringing unit mass from surface to point 3 is nothing but gm by r cube into r square by 2 minus x square by 2. Now this is the work done in bringing a unit mass from surface to this point 3. Okay, what is the total work done by gravitational force from bringing to infinity to point 3? Total work is nothing but work done in bringing from infinity to surface plus work done in bringing from surface to point 3. So total work done is nothing but, what is the work done in bringing from infinity to the surface? Work done in bringing from infinity to surface is nothing but gm by r, isn't it? See, we have already derived it. It is gm by r. Potential is minus gm by r, so work done would be plus gm by r, isn't it? So work done in bringing from infinity to surface is nothing but gm by r, plus work done in bringing the unit kg from surface to point 3. What is the work done in bringing the point charge or point mass from surface to this point inside the space? Is nothing but this variable or this parameter, gm by r cube, r square by 2 minus x square by 2, plus gm by r cube, r square by 2 minus x square by 2, isn't it? Work done in bringing from infinity. See, this is work done from infinity to surface. This is work done from surface to point 3. Okay, understood? From surface to point 3. Okay, now the total work done is nothing but gm by r plus gm by r cube into r square by 2 minus gm by r cube into x square by 2. Now this r square and r cube would get cancelled, isn't it? And it would become r, gm by 2r, isn't it? Gm by 2r. Gm by r plus gm by 2r is nothing but 3 gm by 2r. 1 plus 1 by 2. If you take gm by r common, it will be nothing but 1 plus 1 by 2. 1 plus 1 by 2 is nothing but 3 by 2. So total work done is nothing but 3 by 2 gm by r minus gm by r cube into x square by 2. So this is the total work done in bringing a unit kg from infinity to point 3. So what is the potential? Potential is nothing but negative of this work done. So it is nothing but negative of 3 by 2 gm by r, okay, plus, sorry, to multiply the entire thing by negative, no, minus gm by r cube x square by 2. Now if you take gm by 2r common, okay, I'm taking gm by 2r common, so minus gm by 2r, okay, 3, okay, minus x square by r, gm by x square by r square. Okay, so this is our formula for potential inside the planet. Okay, so if anyone asks to find out the potential inside the planet, this is the formula that you have to use. Okay, so let's move on to the question we're attempting. Okay, The question out here says that we have to find out the potential energy of a particle and the sphere. That means we have to find out the potential energy out here. So what is the potential energy out here? Potential energy out here is nothing but minus gm by r. Okay, the gravitational force with which the sphere exists on the particle. Force is nothing but gmm. Potential is nothing but potential energy of 1 kg. So potential energy of m kg would be multiply the potential by m. Similarly, force is nothing but minus g capital M into small m by r square. Okay, or you have to multiply the mass of the planet by the field at this point. Okay, the gravitational force with which the sphere exists on the particle. So this is simple in nature. Okay. Now I want to see A and B portion of the things are solved. Portion of the question are solved. Now I am to discuss some more about these 3 points. Okay, the point that I made out here. Field and potential outside the sphere, field and potential at the surface of the sphere, field and potential inside the sphere. Okay, outside the sphere this and this, at the surface of the sphere this and this, and inside the sphere it is nothing but this and this. Sorry, inside the sphere it is nothing but inside the sphere field is nothing but given by this formula gm inside by r square, which amounts to this something like this gmx by r cube, where x is the distance from the center. Okay, sometimes instead of using x, few books will also use h. Okay, where h is nothing but depth from the surface of the earth, and the relation between x and h is nothing but x plus h is equals to r. Okay, so out here you can directly substitute x is equals to r minus h, or gm x is equals to r minus h. This much x is nothing but r minus h. Okay, r minus h by r cube, where h is nothing but depth from the surface. Okay, I'm fine. And the last thing was potential. What is potential? Potential inside the planet is nothing but this value, isn't it? Work done in bringing a unit charge from infinity to inside the planet is equals to work done from infinity to surface plus work done from surface to inside the planet. Very fine. Now there are few more parameters or few more variations of the same equation. Okay. The first variation is outside the sphere. Okay, outside the sphere, suppose I'm talking few more variation of the same formula. Okay, outside the sphere. Yeah. This is mass m. Okay, and whenever you have to consider any point outside, the field outside is nothing but distance r. Where r is nothing but distance from the center of the planet. Okay. Now let's say instead of giving you r, they have given you the radius of the planet. Radius of the planet and height from the surface. Okay, height from the surface. What is the relation between small r and capital R and h? It is nothing but r, radius of the planet, plus height is equals to small r, isn't it? Now what is the gravitational potential and field out here? Gravitational field out here was nothing but g into mass of planet divided by r square or small r square, isn't it? Gravitational field out here was nothing but gm by r square. I can also write this gm by r square as gm by r plus h whole square, isn't it? This r square is nothing but r plus h whole square, isn't it? This r square, or I've just substituted the value of r plus h as small r, isn't it? Now if I take common, okay, I'm just taking r common from this denominator. Okay, r into 1 plus h by r, okay, whole square, or f is equals to, I'm separating this r outside the bracket, or I'm bringing this r outside the bracket, right? Gm by r square into 1 by 1 plus h by r to whole square, isn't it? Or this can be written as force is equals to gm by r square into 1 plus h by r to the power minus 2, isn't it? Because 1 by x square can be written as x to the power minus 2. Similarly, 1 by this parameter to the power 2 can be written as this parameter to the power minus 2. Now remember something or recall something. What is field at this point, or what is the value of gravitational field at surface? What is the value of gm by capital R square? It is nothing but 9.8 c mg. The particle is out here, mg. Mg is nothing but the force due to gravity from mechanics or from first two chapters. Okay. Now from the chapter of gravitation, we learn that it is nothing but g mass of planet, mass of E by how much? R square or R plus H whole square, isn't it? And this term can be written as this term, isn't it? So r plus h, or r square into 1 plus h by r to the power minus 2. So this entire parameter and this parameter are the same thing, isn't it? In first three chapters, the value of this g was nothing but 9.8 meter per second square. Okay, and it is to multiply by mass to find out the force due to gravity. And this entire thing is due to force due to gravity. So if I subtract, or if I divide by mass, of the body, I get the acceleration due to gravity, isn't it? Now at the surface of the planet, the acceleration due to gravity is nothing but gm by r square. So at the surface, that means when height is equals to 0, the acceleration due to gravity is nothing but gm by r square. So for Earth, okay, gm by g into mass of Earth by radius of Earth square is nothing but 9.8 meter per second square, isn't it? Force due to gravity, force due to gravity. At the surface of the Earth, force due to gravity is this much. At the surface of the Earth, the value of h becomes 0. Okay. Okay. Now the second point that I will discuss is sometimes, okay, if the value of h is very small, okay, see the planets are very big, okay, radius of the Earth is around 6,400 kilometers, okay, that means it is the distance from here to Russia, okay, or from here to Japan also, okay. So the radius of Earth is very big, okay. So if h is assumed to be 0, okay, I get the formula g mass of Earth by radius of Earth square is equals to 9.8 meter per second square. But sometimes what happens is, suppose we go 100 kilometers, okay, or 200 kilometers, okay. Although the 100 or 200 kilometer from surface is not very less, but compared to the radius of Earth, it is very less, isn't it? So what do we, or what kind of approach do we follow out there? I cannot make h is equals to 0, isn't it? So this same formula, okay, this is the formula for height or field outside the planet. Now, the case is h is very small compared to r. H is very small compared to r, but not small enough that it cannot, means that it is considered to be 0. That means h is very small, but not small enough that you make it equal to 0. So what kind of approximation can we apply out here? For those cases, we just expand this parameter by binomial expansion. Okay, from binomial expansion of 1 plus h by r to the power minus 2, we get 1 minus 2h by r plus higher parameters, higher terms, and we ignore the higher terms. Okay, so this term of 1 plus h by r to the power minus 2 becomes 1 minus 2h by r. So therefore, for the value of h to be very less, okay, when the value of h is very less compared to the radius of Earth, that means the formula of gm by r square 1 plus h by r to the power minus 2 becomes gm by r square 1 minus 2h by r. Okay, now you might have confusion, sir, which formula to use? This formula, this formula, this formula, this formula. Okay, you have arrived with 4 different kinds of formula. This formula, okay, this formula, this formula, then this formula, and this formula. Which formula to use? Okay, see, this formula, and this formula are the same thing, just different different terms. Okay, they are the same thing, and they are the most accurate forms of field. Okay, they are the most accurate forms of formula. This is nothing but the approximate formula. That means only this much is nothing but approximate formula. This out here is nothing but approximate formula. Okay, that means these are nothing but accurate formulas. This is nothing but approximate formula. Now you might ask, when to use accurate formulas, when to use approximate formula. See, the accurate formula is a little bit tough in calculation. If height is given 50 kilometers or 100 kilometers or 200 kilometers, can you do 200 by 6,400 to the power minus 2? It is very tedious, no? Okay, so when the height is more or less 5 to 10%, not 10% is also very large, 5 to lesser than 10%, okay, not 5 to 10%, 1 to 10%, okay, you can use the approximate formula. Listen to me very carefully. Okay, this formula, these three, this one, and this one, are the most accurate terms of field outside the planet. Okay. Problem is the approximate formula that I derived out here by binomial expansion. Okay. And the condition for this approximate formula is h, this height, is much lesser than the radius of the Earth, but not small enough to make it 0. Okay. Then we get this approximate formula. An approximate formula are only used when the value of h is around 5 to 10, not 1 to 10% within the radius of Earth. That means when height is approximately around 1 to 10% radius. Okay, 10% is also a very stretched amount. Just make it 1 to 8%. Okay, you will understand in the question. If it is given 50 kilometers or 100 kilometers, 100 divided by 6,400 is lesser than 10%, isn't it? So you use this formula 200, 300. Now, if the value of height is given as 3,000, isn't it? You cannot use this formula right now. No? Understood? So when the value of h by r, or when the value of h is 1 to 10% the radius of the planet, then you can use this formula. Okay, so this is the first variation or first approximation of the field outside the surface. Okay, the value of gm by r square is nothing but 9.8 for Earth, so 9.8 meter per second square for Earth. Okay, one more thing. See, the field inside the Earth is nothing but gmx by r cube. So I'll do some more thing out here. Okay, field inside the Earth. Or case 3, inside the Earth. Okay, or inside the planet. Inside the planet. Now the formula inside the planet was nothing but this one. Okay, g mass inside by r square. When you solve this one, you get f is equals to gm x. X is the distance from the center divided by radius of Earth or radius of the planet cube. Or f is equals to gm x divided by r cube. Well, r is nothing but the radius of planet. X is nothing but the distance from the center. And sometimes in the formula they use h. Okay. Now for gravitational field inside the planet, there is no approximation. Okay. However, I need to use the variable of h instead of x. So what do we do? R is equals to x plus h. So x is equals to how much? R minus x is equals to r minus h. R minus h. F is equals to g m by r cube into r minus h. Okay. Now g m by r square. This can also be written as F is equals to g m by r square into r minus h divided by r. I have just separated this r cube into r square into r. Okay. If you observe this carefully, this is nothing but 9.8 meter per second square for Earth, isn't it? Gm by r square, or field at the surface of the Earth, this is nothing but 9.8 meter per second square. It is very easy to remember in that way, no? So this is nothing but the value of g. Okay, for Earth, the field is equals to g into r by r is nothing but 1 minus h by r. 1 minus h by r. Okay, so this is one more variation of the formula, that is field inside the Earth. Okay, and this is not an approximate formula, even this is very accurate formula. Okay, sometimes in the question they'll use or they'll ask you what is the ratio of gravitational field 50 kilometer from the Earth's surface to 50 kilometer below the Earth's surface. So that time you have to use this formula and this kind of formula. Okay, so make sure you recall. See, there is only one approximation out here, and that approximation is for case 1, where the field is outside the planet. Okay, the rest are various forms of the same formula. Nothing more, nothing less. But inside of the Earth also, there is no approximation taken. Okay.